Okay, so we're here once again for this course, temperature and pressure in physics. Let's, without rigmarole, let's start. Can you hear?
Yes.
Okay. Can you see the screen?
No.
Okay. Wait. Let's share. Can you see?
Yes.
Okay. Now let's take it. Today we're looking at 2.1.3. Never mind the designation for the subtitle. It's just used in this way. Remember, we're doing thermophysics, and now we're looking at temperature and pressure. Now let's take a look at temperature and pressure. First and foremost, let's look at the motion of particles in gas, right? You know, molecules in a gas, they are always in a random motion. They are in constant zigzag random motion. The molecules are moving in all directions. Okay, they are moving in omnidirectional. They're moving in all directions. The molecules are moving randomly, zigzagly, colliding with themselves, colliding with the walls of the containers. You know, this is the pattern, this is the nature of the movement of molecules of gases in any setting. Is that okay? And they do this, while they do this, they move at very high speed. They are always moving at high speed. Now, this random motion, what it means is that the molecules are traveling in no specific path or pattern. They undergo sudden changes in their motions, they collide with themselves, they collide with the walls of the container. Look at it, look at the diagram, okay? These molecules, they can bump onto themselves, bump onto the walls of these are the walls of the container, right? These are the walls of the container. You can see this molecule can hit the wall and bounce off. You see, this particular molecule hit this wall, right? And then bend it to this direction, meaning it's bouncing off. This one can come and hit this one so that this one can hit this, like that, in a very random manner. This one hit the edge here, then is going this way. Okay, it's bouncing off. So it's a continuously. They're moving randomly, they are moving zigzagly, and so on and so forth. Is that okay?
Yes.
Okay. So that's the concept. They're moving in a very unpredictable manner and path. Okay, they move, they change, they collide with themselves, collide with the wall, and like that, bounce off, bounce here, like that. Okay, so they bounce off when they hit themselves, they hit the walls of the container, and they also hit themselves, they hit one another. Okay, this is the collision. The collision is among themselves, they hit themselves, and another thing is that they hit the walls of the container. So in a gas, or the pressure in a gas is caused by what? By the collisions, right? When pressure is as a result of collision, remember, pressure is force over an area. That's the concept of force, of pressure. Pressure is whenever a force is exerted over an area. So when a molecule hits the wall, that's already a force, right? A force. Over where? Over an area, a specific area, because it's hitting a specific spot. The molecule is hitting a specific spot, right? It hits a specific spot. So there's a force over an area. That's what we call gas. Anytime there is force over, so collision results to pressure. Collision results to pressure. The greater the rate of collision, the greater the pressure. The greater the collision, the greater the pressure. The faster the collision, the more the collision, the greater the pressure. So if that's why we say temperature can increase the pressure. If you hit this molecule, they will be moving faster and be hitting themselves very fast, and they will hit the walls of the container super faster, right? They do this at ease. They will hit themselves with ease. They hit the walls of the containers. They hit the walls very fast. So whenever a molecule, this ball, this blue ball is like a molecule. It's a sample of a molecule. When it hit the wall, that hitty, slap, hitty, kick, push, pull. These are all forces. These are all descriptions of forces. So when you hit something, that's a force. Okay. So when the molecule hit the wall of the container, that's a force. Then it's hitting a particular spot, that's an area. When you hit a spot, that's an area. If you touch somewhere, the place you touch is the area, is the surface area of that place. So the force divided by the area becomes the pressure. The force divided by the area becomes the pressure. And you can increase the pressure by increasing the collision or by increasing the rate of collision. And how can you increase the rate of collision? By increasing the kinetic energy of the molecule. And how can you increase the kinetic energy of the molecule? How can you increase the kinetic energy of the molecule? By increasing the temperature. So temperature, if you increase temperature, you result in increasing the average kinetic energy of each molecule. Once the kinetic energy, the molecule gain kinetic energy, then they will move faster, they will collide faster, and it will result to greater pressure. It will result to what? Greater pressure. Are you with me?
Yes.
Okay, so this is what happens. This is what happens, what you see, especially in the case of Brownian motion. We're going to talk about Brownian motion after this section. After we finish temperature and pressure, the next segment will be the Brownian motion in thermophysics. Is that okay? Now,
Yeah.
before then, let's quickly take a look at the pressure and force of particle in a gas, which I have technically explained. I have explained the pressure. I say it's as a result of force divided by area, right? That's what pressure. And what increases the force is the kinetic energy. And what increases the kinetic energy is the temperature, right? So because when you increase temperature is from heat. When you heat the molecules, when you supply heat, the temperature might increase, right? So definitely increase. So when the temperature increases, the molecules will gain kinetic energy. The moment you gain energy, you can act faster. For example, let's say you are playing soccer, okay, and then you became tired. You see, they give them water to drink, they give them energy boost. They drink during halftime. You go for halftime, you can take 1 or 2 Lucozade boost, energy boost, any glucose given solution. You can drink to boost your strength so that you can face the match more, right? Right?
Yes.
Even in school, why do we have breaks? Why do we have break in school? In school, before 2:30 or before 4 o'clock, you see some schools, they close by 4, some close by 2:30. Before then, you have like 2 breaks. There's a break around 10:30 or 11. There's another break around 12 something. Why do school have breaks? So that the children can go and take some food and be energized and be focused, super focused. So same with molecules. Molecules needs to be energized. Their energy needs to be increased. This energy is called kinetic energy because kinetic energy is the energy that keeps the molecule in motion. The energy the molecule possesses when it's moving. The molecule needs to move and they need kinetic energy. To get kinetic energy, you have to increase the temperature. Once temperature is increased, these molecules, they will gain what? Average kinetic energy. Now this energy is sufficient to keep them moving. And when they move, what happens? Because they're moving randomly, they don't have a path. They don't have a specified direction. They move randomly any direction. So they can hit themselves and they can hit the walls of the container. They can hit themselves and they can hit the walls of the container. Are you with me? They can hit themselves and they can hit the walls of the container. And when this happens, then we say a force is exerted over an area. When they hit the walls of the container, we say a force has been exerted over an area. That is called pressure. Because pressure is force per unit area. That is called pressure. Because whenever a force is exerted over an area, then that results to what we call pressure. That results to what we call pressure. And this is the modeling. This is the modeling. All that I have said is put into a mathematical formula, which is shown below. First, before we talked about the formula, we say P is pressure, and the unit of pressure is Pascal. You can see in bracket. The unit of pressure is Pascal. We put it in a bracket. And the force, the force the unit is what? F is force, and the unit is a Newton, N in bracket. A is area, and the unit is meter square, right? Now, before we talk about this, let's say that a feature of gas is that they fill the container. You know, this is one of the features of a gas. If you put a little gas in a container, it's going to fill it up. It's going to fill it up. Why? Because the pressure is increased. Pressure is force over area. The molecules are moving and bumping everywhere. So they're going to occupy the whole place. They're going to fill up the whole place. Is that okay? Gas particles, as they move about randomly, they collide with the walls of the container. So, because they collide with walls of the container, they exert a force on the wall. And that force over the area they hit, the spot, the surface area they hit, the molecule hits, is called the area. So that force per unit area is defined as the pressure, right? The collision produces a net force, which we have already talked about. The collision produces a net force at right angle to the walls of the gas container, right? At right angle to the walls of the gas container. So a gas at high pressure has more frequent collision. A gas at high pressure has more frequent collision. And what could have resulted to more frequent collision is that the average kinetic energy of the molecule has been increased. And what could have increased the average kinetic energy of the molecule? Usually the temperature. Okay, temperature increases the rate of collision of the molecules, and hence increases the net force, hence increases the pressure of the gas. Is that okay? Now we say the higher the pressure.
Can you repeat?
Okay.
That?
Okay. I said that when you increase the temperature, the molecule will gain more kinetic energy. When you increase temperature, the molecule will gain more kinetic energy. Are you with me? Hello?
Yes.
Okay, when you increase the temperature, the molecule will gain more kinetic energy. And once they gain more kinetic energy, then the molecule will move faster. You know, the energy will enable them to move very fast. And once they move faster, once their speed increases, because the kinetic energy will increase their speed. Once the molecule increases their speed, they can collide more frequently. And when they collide more frequently, then there is more force over an area, then there is greater pressure. That results to greater pressure. Is that okay?
Yes.
Okay, take a look at this diagram. Can you see this diagram?
Yes.
Okay, you see the molecule they hit this surface. Let's say this black line is the thick black line is the wall of the container. The molecule hits it, see it bounces off. This one hits here, it bounces this way. This one hits here, it bounces this way. This one is coming also to hit. This one will hit here. So wherever you hit, that's a force. Hitting is a force. Just like slap is a force. Slap is a force. Clap is a force. Push is a force. Pull is a force. Hitting is a force. So when the molecule hit the surface, that's a force. And it has also hit a spot. That spot is an area. That place it hit is an area. Are you with me?
Yes.
Okay. So it is possible to experience this force by closing the mouth and forcing air into the cheek. You can close your mouth and force air into your cheek. You can experience a force. Okay? Anyway, that's just by the wayside. Now let's move on to the next subtopic, which is Brownian motion. Okay, you know, in describing Brownian motion, this Yugo scientist, what he did was he took some smoke particles and air molecules and put them in a container. And he used a microscope to view them. He shone light into them. He shone light into it from one direction, and used a microscope to look at what is happening between the air molecules and the smoke particles. And then he found out that they were bombarding themselves, they were hitting themselves from all angles, from all directions, from all corners. And then they were moving randomly, zigzagly in a very unusual manner, undefined path. They were moving in a very undefined path. So he came up with this, and this Brownian motion explained this concept of the random and constant random motion of molecules. Remember, the atmosphere, the air is made up of billions and billions of molecules. Even the smoke is made up of millions and millions of particles, right? So this Robert Brown is a scientist. He's from Scotland. Robert Brown is a scientist from Scotland who carried out this experiment, and he gathered that you can see. The first one he did was the random motion of polygrains in water. The first one was the random motion of polygrains in water, which he saw under a microscope. He viewed them under a microscope. The polygrains in water and the way they were moving randomly, and he viewed this under a microscope. But before we expatiate on that, you have to remember the kinetic theory of matter. Remember the kinetic theory of matter, right? Before you can begin to understand this concept. The kinetic theory of matter simply says that all matter is made up of tiny particles. All matter is made up of tiny particles. All matter is made up of tiny particles. Are you with me?
Yes.
All matter is made up of what? Tiny particles. And that these tiny particles are always in constant and random motion. Okay? All matter is made up of tiny particles. Any matter, whether it's in a solid state, liquid state, and gaseous state, they are all made up of particles. Is that okay?
Yes.
Okay. Now, the observation that this scientist, Robert Brown, observed when polygrains were bombarded in water, what he saw under a microscope, the observation could not be explained at that time. What he saw, he couldn't explain it, right? But later it was realized that it shows that substances are made up of particles which are in constant motion. Hence, they are kinetic, because when you're in motion, that's kinetic. Okay, so it was later realized. Okay, but at that time, what he observed, what he saw under the microscope, he couldn't vividly explain the concept. So this, what you see in this is Brownian motion. You can see the polygrains moving in all directions, zigzagly, anyhow. This one goes here, goes here, goes here. You know, they just move it. They can hit themselves, hit the water molecule, hit the walls of the container, like that. They're moving very randomly. So the guy was confused somehow. He couldn't know. He didn't understand. He didn't know how to explain this concept. What he observed, what he has seen. Okay, so. But later, scientists were able to understand this particles movement and explain what Brownian has observed, what he has seen. So the Brownian motion is the random movement of the particles in a liquid or in a gas. So simply put, the Brownian motion is the random, random. Random is like anyhow movement, all direction, go here, go up, down. You don't really have a specific direction or a specific path. That's the meaning of random motion. Are you with me?
Yes.
So the random motion is simply the Brownian motion. Brownian motion is simply the random movement of particles in a liquid or in a gas, produced by large numbers of collisions with smaller particles, which are often too small to be seen by our eyes. Like another example is air molecules and smoke particles. I give you another example. Sometimes in the daytime, when you sweep your room, you open your windows, you let the sunlight shines into your room, you see dust particle moving in the direction of the light. You see them moving zigzagly, right? Every one of us have probably have observed this. So this is a Brownian motion concept. Okay, you can see that the air molecules moving randomly because light has been shown into your room. You could see the random movement of the dust particles in your room moving zigzagly, right? That's another example.
Yes.
That's another example. Is that okay?
Yes.
Okay, so we've simply put the Brownian motion as the random movement of particles in a liquid or in a gas. And this produces a large number of collisions with the smaller particles, because in this case you have usually we have two concepts, two molecules. One is a molecule, the other one is a particle. One is smaller in size, the other one is larger in size. So they collide with themselves, bounce off, and so on and so forth. Now, this is a smoke particle, for example, for instance. This is a smoke particle. Why this is this large one is a smoke particle. These tiny blue small ones are air molecule or gas molecule. You can say gas molecule or air molecule. So this smoke particle and gas molecule are subjected together in a tube or in a container, and then we shine light to it. Then you view with a microscope, you can see the bombardment and the random movement of the air molecule with the smoke particles. Is that okay? This is what we have the occlusion. This is the large particles put here. You can see the smoke particle as the large one, and then the small one may probably the gas molecules or the air molecules. So the small, faster moving particles are also put. These smaller ones, they move faster and they can collide with the large one to push them off in any direction. In any direction. Is that okay?
Yes.
Now let's take a look at it for the extended concept. Now when observing the Brownian motion, even with a microscope, only the microscopic particle can be seen. Only the microscopic particle you can see. Even if you use a microscope, it's not everything you can see. The tiniest one, you may not even see them with a microscope. The poly or the smoke particles are seen to move, right? The poly or the smoke. Because, for instance, the poly, they are the larger particles in the case of water and poly. Then, in the case of smoke particle and gas molecules, then the smoke particle is the larger one. That's what this one can pick, the microscope can pick. The microscope can see the larger molecule, but probably may not see the tiny particles that is bombarding when I say bombard, that is hitting the large one. Is that okay?
Yes.
Okay. So the poly or the smoke particles are seen to move. The small atoms or molecules from air or from water, okay, are still too small to be seen by the microscope. They're still too small to be seen. Is that okay? But once we see the large one moving, we know it's the small one that collided with them. And that's why you see the movement. Is that okay? So the light, fast moving atoms and molecules collide with the large microscopic particles to cause that movement that you see in the larger particle, like the smoke particle or the poly. Is that okay?
Yes.
The smaller atoms and molecules of water and air, they are too small, right? We probably don't see them, right? This collision gives the particles a little nudge, causing them to change their speed and to change their direction and in a random manner, in a zigzag manner, right? They cause these particles to change their speed. That's the atoms. These small ones are the atoms, the air molecules. Okay, they are atoms or molecules. You can call them atoms or molecules. These small air molecules or water molecules, they are fast moving, right? We've established that, and they collide with the smoke particle or the poly particles, right? Causing them to change their speed, causing them to change their direction. Okay, maybe they were moving very slowly. When they hit them, they start moving a bit faster, and they may be moving in another direction depending on the direction upon which they were hit. So they will start. So the atoms, these small atoms, the air molecules or atoms, or water molecules or atoms. So we're using two examples now. Either you use water or use air as the tiniest part, for these tiny particles. Either you use water or you use air for these tiny particles. Now these tiny particles, which is either water or air, they can hit these large particles, which is either poly or smoke particles. So when they hit them, they can cause them to change their direction. That's one. They can also cause them to change their speed. Maybe their speed was slow. When they hit them, they can cause them to move faster. In a very random way, not in a specific way. Random means in anyhow direction. In any direction.
Yes.
Okay. So in a very random way, not in a straightforward way, right?
Yes.
Now, the presence of light, a fast-moving atoms and molecules is infrared from the motion of the microscopic particles. Inferences such as these are important part of scientific investigation. Let's see if we have a diagram to illustrate this. Okay, I think the diagram was not displayed here. But when you open your textbook, you see this is actually the diagram, but I wanted to show we can connect a microscope on top to view this, and then we shine light from this way. Can you see my arrow? Like the way I'm
Yes.
moving the mouse? You can see, right?
Yes.
So this way we shine a source of light to look at this glass tube. Let's assume this is a glass tube. We shine light from this left side into this glass tube, and then we put a microscope on top, and then we put our eyes on the microscope to view what is happening inside here. That's how this observation was obtained. Are you with me?
Yes.
Okay, now let's move to the next one. We still can do one more, right?
Yes.
And let's go to the 2.15, which is gases and absolute temperature. Gases and absolute temperature. Here we're going to learn some formula. We're going to send the notes like we've always done, okay?
Okay.
Gases and absolute temperature. Now, what is absolute temperature? The Kelvin temperature scale begins at absolute zero. Absolute zero is absolute zero, which is 0 Kelvin. You know, first of all, temperature is the degree of hotness or coldness of an object. Did you get that? The word temperature, what does it mean? Temperature is the degree of hotness or coldness of an object.
Yes.
If something is hot, you say, oh, the temperature is low. If something is If something is cold, you say, oh, the temperature is very low. If something is hot, you say the temperature is high. Okay? We even have negative temperature, like -5, -10, like during winter in some countries like Russia, Sweden, Finland, Norway, or the Scandinavian countries in Europe. The Scandinavian countries in Europe during winters, even up to Asia here, like China, the countries in the North Pole, around the North Poles of the world, like China, like Japan, okay,
Yes,
Japan,
yes.
South Korea, North Korea, they are also in the northern hemisphere of the world. So these countries that are in the northern hemisphere of the world, like okay, in America you have Canada, and then you have US, a bit of US, okay? The top part of US, the north of US, like the New York area, the Pennsylvania area, like the Washington area, not the Washington DC, you know, there's also a state in US called Washington. Like the Washington, all those in the northern hemisphere, the north part of US. And then in Canada, there's the whole of Canada up to the north, but it's worse in the northern part. Then you come to Europe, all the countries, especially the Scandinavia countries and all the countries in the north hemisphere, like the UK, a little bit of it, but UK is not super up, but it's a bit up, okay? It's a bit up. So,
Okay.
So, but countries like Sweden, countries like Denmark, countries like Finland, countries like Norway, countries like Denmark, Finland, Norway, okay, Russia. Then we come down to Russia, and then you come to Europe, Asia. You can talk about just a minute, okay? So
Okay.
just be thinking of countries that during winter they have what? Negative temperature. They have negative
Okay.
temperature. These countries they have negative temperature. Are you with me?
Yes.
Okay. So what does it mean to have negative temperature? What does it mean?
It's how it's cold.
Yes. It means it's very cold.
Cold.
Yeah. It means it's very cold. Right?
Yes. Okay.
It means it's very cold. It means it's very cold. Right? Just a minute, okay? Just a minute.
Okay.
How about the website? Can I have the website? No, for Sally. Uma doesn't have exam. Is that for Sally? I mean, it's the first time for Sally because Uma, they have normal class. And then can you also have the website because the exam is waiting, like, or do they need to look up for themselves? Okay, but then for the website that they should join, did they send it to you, or did they look for it from the for themselves?
Okay, let's continue. Sorry for that 1 minute break. I have to respond to an emergency. Okay, now let's take a look at what we have here. We say that a temperature. We're talking about temperature. That is the degree of hotness or coldness of an object. Then we mentioned that temperature has both positive integers and negative integers. We say temperature has both positive integers and negative integers. What I mean by positive integers means the positive whole numbers. Positive whole numbers. And then we say they also have negative integers, right? Which are negative whole numbers. So we said that we even said during winters, during this time, November, December, during December, January time like this, then most countries in the northern hemisphere of the world, they experience negative temperature. We were naming these countries. We were looking at some of these countries that are super cold. So in fact, if you go to the Arctic tundra, there is the Arctic tundra, which is even worse than the countries that we just mentioned. Okay, these countries are very close to the pole, the North Pole itself. The Arctic tundra, that region is very close to the North Pole itself. The temperature is way negative, more than negative 50, negative 18 of those regions. And some countries like Canada, their temperature, or Russia, their temperature can get to negative 40 or even more than that, okay, during winter. So now we understand the temperature, what it means. That is the degree of hotness or coldness of a body. And we also said that these numbers could be positive and as well as negative, being negative numbers. And then we said this temperature has a unit, just like we said the unit of force is Newton, the unit of pressure is Pascal, the unit of speed is meter per second, the unit of, everything in physics or in science, physics specifically, has a unit. Every physical quantity has a unit. Now, the unit of temperature is actually Kelvin, but both degrees Celsius can also be used and Fahrenheit can be used, okay, as units or subunits of temperature. But the absolute unit, the what do you call this body that regulates the unit? International System of Unit. Okay, the International System of Unit, IS units, adopt Kelvin as the unit of temperature. Adopt Kelvin as the unit of temperature. So we're going to learn, later we're going to use a formula to relate how you can convert temperature in degree Celsius to Kelvin. That is very paramount. That's the first thing you learn here. It's very paramount. How you can convert temperatures in degrees Celsius to Kelvin, and temperature in Kelvin to degrees Celsius. And then we're also going to learn how to do conversion from temperature in Fahrenheit to degrees Celsius and temperature in degrees Celsius to Fahrenheit. And temperature in Kelvin to Fahrenheit temperature. So we're going to learn all of this. But before we begin, there's what we call in Kelvin scale, because temperature, we're going to learn the different temperature scales. Temperature have about 3 different scales. The first one is the Celsius scales. The Celsius scale, I don't know if this concept takes a holistic look at it. The Celsius scales takes a look at from 0 to 100 degrees Celsius. Okay, we have the lower fixed point and the upper fixed point. The lower fixed point is the 0 degree Celsius, which is the melting point of ice or the freezing point of ice, the freezing point of water. So the lower fixed point in a temperature scale, looking at Celsius scale, okay, looking at Celsius scale, we have the lower fixed point and the upper fixed point. In between the lower fixed point and the upper fixed point, there are 100 degree divisions. So we have the 0 degree, you have 1, 2, 3, up to 100. So the 0 degree is the lower fixed point. The 100 degrees Celsius is the upper fixed point. Or the upper fixed point is also called the boiling point of water. It's called the temperature of the boiling point of water. Are you with me?
Yes.
Okay. Now that's for Celsius scale. We've not come to Celsius scale. Let's take a look at Kelvin scale. For Kelvin, it is not possible to have a temperature lower than 0 for Kelvin because 0 degree in Kelvin is equivalent to minus 273 for degrees Celsius. We're going to look at this, how this plays out. Okay, 0 degree is 273. Now minus 273. We're going to look at this. Okay, Now, this means that a temperature in Kelvin will never have a negative value, but not in degrees Celsius, okay? Remember, in degrees Celsius, we have negative values, but in degree Kelvin, everything starts from 0 and moves upward in the positive direction, positive integer numbers. Now, this means a temperature in Kelvin will never have a negative value. Now, to convert between temperature, we use theta, these symbols. Can you see these symbols? This symbol, this one, sorry. I'm trying to highlight it. Can you see the symbol I highlighted?
Yes.
Okay, it's called theta. We use it as a symbol for temperature, to represent temperature. Okay? Or sometimes in some text, we use T. We use letter T, capital letter T, in some text. So we say, to convert between temperature, that's theta in degrees Celsius, and T in Kelvin. So in degrees Celsius, we use theta. In Kelvin, we use capital letter T. So this is the formula that we use. So temperature in degrees Celsius is equal to, look at the formula, the first formula. Can you see the first formula?
Yes.
Look at,
Yes,
I've
sir.
highlighted it. Temperature in degrees Celsius is equals to temperature in Kelvin minus 273. What if the temperature is in Kelvin, we want to change it to the sensors. Let's say I say a substance has a temperature of 298 Kelvin. What's the temperature in degrees Celsius? So you say, to change it to degrees Celsius, you say this 298 minus 273. Or let's say 300. 300 minus 273, what will you get?
300.
It's just like, 300 minus 273. It's just like saying the remaining 100. You know, you first of all say 300 minus 200. You get 100 left. The remaining 100 minus 73, what will you get? You get 27. So the answer will be 27 degrees Celsius. For example, if I tell you a substance has a temperature of 300 Kelvin, what is its temperature in degrees Celsius? So to change it, you use this formula. You say temperature in degrees Celsius is equals to temperature in Kelvin minus 273. In the real value is actually 273.15, but when you get to higher level, you will be using that point. But for now, we just round it to the nearest whole numbers. The nearest whole number. Is that okay? 273
Yes.
to be precise. Okay, now, then vice versa, if you're giving a temperature in degree Celsius, let's say I say the temperature, your room temperature right now is 28 degrees Celsius, for example, or 25 degrees Celsius. Okay, let's say that there's a temperature we say the temperature of your room is 25 degrees Celsius, or right now it's a bit cold, right? Let's say it's 20. Your room temperature right now is 20 degrees Celsius, for example. Now, what is the temperature in Kelvin? What's the value in Kelvin? What's the value? The temperature in your room right now is 20 degrees Celsius. What is the value in Kelvin? So, if you want to change to Kelvin and you are giving degrees Celsius, you know degrees Celsius is when you write small degree, small zero, then you write big C, small zero on top, then before you write big C, right? Look at it
Yes.
like here, like the way you see it. You see small tiny zero on top. That tiny zero on top is degree. So when you say to change 20 degree to Kelvin, you say 20 plus 273. You just add the 20 to,
293.
yeah, it will be 293. 293. You just add 20 to 273 to change to Kelvin. It will be 293 will be the temperature. So it means your room now is 293 Kelvin. It means it's 293 Kelvin. Is that okay? So,
Yes.
and for this is the comparison between the two scales. This is called the Celsius scales. They put together in one diagram. Look at it. We have the Celsius scale on the left. Okay, actually sometimes we draw them separately, but I like the way this is drawn together, put together. Okay, this is degrees Celsius, and on the left is temperature in Kelvin. On the right is temperature in degrees in Celsius. Celsius scale, yeah. On the right is Celsius scale, on the left is a Kelvin scale. Okay. Now you can see that on Celsius scale 0 degree, which is the melting point of ice, is exactly 273.15. You know, I told you the exact value is 273.15. Okay. So if you minus 73 is 200, minus 173 is 100, minus 273 is 0 for Kelvin. So you need to understand this conversion. You need to know this diagram very well. You need to know it very well. Okay, let's hurry up and round up here. Okay.
Okay.
So here is an example which you're going to do when. Okay, let's take a look at this example quickly. Convert the following values between the Kelvin and Celsius scale of temperature. Convert the following between Kelvin and Celsius scale of temperature. 0 Kelvin will be what in degrees?
-273.
Yeah. 0 Kelvin will be. 0 Kelvin will be.
-273.
0 Kelvin negative
273.
negative.
Celsius.
Yeah, I know you are right. I'm talking to Amin.
Yes, negative.
Yeah, negative 273. Now, what of 0 degrees Celsius? 0 degrees Celsius will be what? Now you are converting to Kelvin. You just add 273 to it, right? If you are converting to Kelvin, so it will be 273 Kelvin, not negative. 20 degrees Celsius. Oh, I've done this example with you guys without even knowing they're going to give this example.
Yes.
20 degrees Celsius to Kelvin, you just add 273, you get 293, right?
Yes.
So these are the work. These are the examples. These are the solutions. For the
Yes.
first one,
Kelvin.
minus 273. The second one, 0 Kelvin, is negative 273. Okay. The second one, 0 degrees Celsius is 273 Kelvin. And the last one, 20 degrees Celsius is 273 Kelvin. Okay. Here comes the gas law. Because I really want to quickly stop. There's something I need to do. Okay, can we take this gas law in another time?
Okay.
Let's take this gas law because this one will lead us to Boyle's law. Maybe can we meet again later in the evening? Can we have so that we can finish this part?
Okay.
Okay. Thank you.
What time?
I will communicate you guys. Okay.
Okay.